The pendulum. The first harmonic oscillator used by man. Being the object that regulates the mechanism of a clock, it is the ultimate symbol of time passing, of inevitable change. But what if we oriented it to be upside down? Would it stabilize and thus be able to function as an inverted pendulum? No, it doesn't. That didn't work at all. But what if we, vibrated this inverted pendulum vertically at a high frequency? What would happen then? Why, it's working. It's actually stabilizing. It's beautiful. But how on earth did vertically driving the inverted pendulum at a high frequency stabilize it? If only I understood the classical mechanics that explains this phenomenon. Oh wait, I do. Let's do some math. The motion of the pendulum can be described by deriving a differential equation from the Lagrangian. This can be found first by defining the coordinates in terms of the angle the pendulum deviates from the vertical, as well as the driving frequency and amplitude. Then, by defining the kinetic and potential energy in the x and y direction in terms of theta to get your Lagrangian. And then, you use the Euler-Lagrange formula to find your differential equation for an inverted pendulum in terms of theta. Cool! It seems like if the driving amplitude times the driving frequency squared exceeds the value of the gravitational constant, this term would dominate the acceleration in the theta direction. In other words, if the driving frequency is fast enough, the inverted pendulum should stabilize. Does this mean at lower driving frequencies, at the same driving amplitude, this inverted pendulum becomes unstable? Let's see. Fail! Something that might help us to visualize why this happens is by observing the potential energy of the mass on the end of the pendulum within the effective potential energy well of the system. This effective potential energy well is derived as a function of x to keep this visual in the xy plane, to thus display the potential energy's relationship to the actual motion of the mass most successfully. We can see in the situation with slower driving frequency, the system becomes unstable with gravity, which eventually overcomes the motion of the mass despite the vertical vibration. It looks so hopeless. But with the higher driving frequency, we see that though the gravity destabilizes the system, the oscillation due to the vertically driving the pendulum at a higher frequency stabilizes it before gravity overcomes the mass. What a miraculous phenomenon! You may be wondering at this point, I know I sure am. What happens if we apply the same vertical driving force to a normal pendulum? Well, guess what? I already know, and it's super boring, except when your driving frequency is equal to twice the effective natural frequency of the pendulum, which for pendulum it's the square root of g over L. See for yourself. As you can see, the system exhibits parametric excitation, that its amplitude increases exponentially with time. Until the length of the pendulum, which restricts this excitation, brings the oscillations nearer to the equilibrium position again. But just to be parametrically excited once more! The differential equation for this system is very similar to the previous differential equation for the inverted pendulum, except that the sign of the two terms are switched. The gravity, in this case, is what stabilizes this pendulum. We can see the reasoning behind this excitation best simply through a conceptual analysis of the simulation. You can see that the driving force is able to do the most work on the system when theta, the angle the pendulum deviates from the vertical, is 0. This means we will get a maximum response if the vibrating support moves upward each time the mass passes theta equals 0. In this case, the period of this vibration will be half the period of the pendulum, since the pendulum passes theta equals 0 twice per period of its oscillation. Thus, we see parametric excitation when omega drive is twice the natural frequency of the pendulum. For funsies, let's observe this behavior through the effective potential energy well for this system, as we did with the inverted pendulum. As much as we have learned in these short 7 minutes, I think it is pretty clear what the most significant discovery of all has been. The discovery of the greatest dance move ever known. The vertically driven pendulum.